Hello guys, my name is Wahid. Welcome to this review session. Primary Cisco Enterprise Architecture modules include Enterprise Campus, Enterprise Edge, Service Provider Edge, and Remote. So we have 4 primary modules with Cisco Enterprise Architecture. Each of these modules, they have a number of components associated with them. Enterprise Campus, the components include end users and devices, server farm, building, access, distribution, core layers. These are different components of Enterprise Campus module of Cisco Enterprise Architecture. Components for Enterprise Edge module includes e-commerce, internet connectivity component, remote access, and site-to-site VPNs. Enterprise Architecture, the third module, is Service Provider Edge, and its components include ISPs, PSTN, Frame Relay, ATM, and PLS. So they are all under Service Provider Edge. And fourthly and finally, we've got remote component of Enterprise Architecture, remote module, and remote module includes these components: Enterprise Branch, Enterprise Teleworker, and Enterprise Data Center. You may be asked about different components and how they come under different modules of Cisco Enterprise Architecture. For instance, we can say Enterprise Campus. It provides access to the network, communication services, and resources to end users and devices. The primary Cisco Enterprise Architecture modules, they cover two different architectures. A two-tier hierarchical called collapse core is when the distribution core layer functions are implemented by a single device. So merging distribution and core together. It is used by smaller businesses in order to bring down network costs while maintaining most of the benefits that we have with a three-tier core distribution access hierarchical model. The access layer grants end devices access to the network, as you expect. In one environment, it may also provide teleworkers or remote sites access to the corporate network across one connection. The access layer serves a number of functions, and it's important for you to remember these functions which are served by access layer. Functions include layer 2 switching, as you would expect. Quality of service classification and marking is also done by access layer. Port security or ARP, address resolution protocol inspection, power over Ethernet, these are all functions to be served by access layer. But access layer does not provide redundancy. We don't have redundancy there, or it does not provide load balancing. So it's the job of distribution of core layers. So remember which functions include and which functions are excluded from the responsibilities of access layer. We should know about IPv4 and IPv6, and also we need to see how different routing protocols are dealing with IPv4 and IPv6. We have distance vector routing protocols. For IPv4, we have RIP version 2, we have EIGRP for IPv4, and we have distance vector routing protocols for IPv6. So we've got RIP-NG which is RIP next generation, and also we have EIGRP for IPv6. We've got link state for IPv4. We have OSPF version 2 and ISIS for IPv4, and then for IPv6 we have link state routing protocol OSPF version 3, and also we have ISIS for IPv6. Then we've got exterior gateway protocols, path vector routing protocols type, and for exterior ones, for IPv4 we have the famous BGP version 4, BGP4, and we've got for IPv6 MP BGP, multi-protocol BGP. We should know about different address types that IPv6 supports. IPv6 supports 3 address types: unicast, multicast, anycast. We don't have broadcast in IPv6, remember that. So IPv6, 3 address types: unicast, multicast, and anycast. What you can see in this slide is the IPv6 access control list, ACL. Unlike IPv4, whereby we have both named and numbered access control lists, with IPv6 we only have named access control lists. So IPv6 access control lists are named only, and that is similar to extended IPv4 access control lists. Similar to IPv4, however, IPv6 access control lists are also applied on interfaces, inbound and outbound, with in command or out command, depending if you want it inbound or outbound, but on the interface configuration similar to IPv4. The command that you need to use in order to apply named access list, access control list, named IPv6 access control list is IPv6 traffic filter, and then the name of that IPv6 access control list that you have allocated to the named access control list. So traffic filter, remember, IPv6 traffic filter name is the command that you need to provide under the interface, either inbound or outbound. Also remember that we have time-based access control lists. So time-based access control lists. So with time-based access control lists, we can have 2 different types. We can have periodic. With periodic, we have access lists being activated and deactivated at a specific time of a day, week. Second type of time-based access control lists are absolute ACLs. Absolute ACLs, whereby access control lists can be configured to start and stop at fixed configured time. Similar to IPv4, here with IPv6 access control list, we can have the time-based access control list, and to have that, at the end of the permit or deny statement, we just provide the name of the time-based access control list, the time range that we have defined previously. So we first define a time range and give it a name and specify if it's periodic or if it's absolute, and then that name given to that time range will appear at the end of the permit or deny statement with IPv4, IPv6 access control list. And this way we can have time-based access control lists. Recall that with IPv4 you had implicit deny at the end. With IPv6 we have 3 different statements, not only one. We have permit ICMP any ND neighbor discovery, NA, and also NS. neighbor advertisement, and neighbor solicitation. So these ICMP version 6 message types, they should be allowed, and that's why we need these two parent statements, and then we can have deny IPv6 any. So these three are implicit rules that we have at the end of each access control list for IPv6. We don't see them, but they're already there. They will be applied. Why should we have NA and NS permitted implicitly at the end of each access control list? Because in IPv6 we don't have ARP, and we have NS and NA working what ARP used to do with IPv4 now in IPv6 for us. So we have neighbor solicitation sent by device to solicited node multicast address when it knows the IPv6 address of a device, but it doesn't know the Ethernet MAC address associated with that. So this is exactly what ARP used to do in IPv4. We do it here with neighbor solicitation message. So NS sent by device to solicited node multicast address. And in response to NS, device is supposed to send us NA, neighbor advertisement, where we're going to have a response to an NS message previously sent by us. Next up is Path MTU Discovery PMTUD. It was developed, in fact, in order to determine the lowest MTU along a path from the packet source to the packet's destination. So that's the purpose for it. We have this concept with IPv4, not IPv6. With IPv4, PMTUD is only supported by TCP and works by setting the DF flag, don't fragment flag. This flag is in fact one bit inside IP header, so we set DF flag bit in IP headers of outgoing packets. What would happen at the end of the day is that any device along the path whose MTU is smaller than the packet, the one that we just sent out by setting the DF flag bit, any device, once again, along the path whose MTU is smaller than the packet will drop it and send back ICMP fragmentation needed message type 3 code 4. So this is one particular ICMP message that we're looking for as a response from that node that drops the packet due to smaller MTU supported. So it sends back an Internet Control Message Protocol ICMP fragmentation needed message containing its own MTU, which is the smallest one or smaller one at the moment, allowing the source host to reduce its path MTU appropriately. This process is then repeated and repeated until the MTU is small enough to traverse the entire path without any fragmentation needed. So this is the job of PMTUD thanks to don't fragment DF flag bit in IP header. It is important to remember that the ICMP fragmentation needed message, which is issued as a result of a node whose MTU is smaller than the packet, and therefore the packet is dropped by that node. That ICMP message also contains, or additionally contains, its own MTU. Therefore, the source host knows how to react and how to reduce its path MTU appropriately. This protocol is called Path MTU Discovery PMTUD. Recall that I told you IPv6 behavior towards a large MTU is different. How is it different? If an IPv4 router receives a packet with larger MTU than allowed in segment and therefore fragmentation is enabled, IPv4 router itself will fragment the packet in smaller pieces and forward them. So with IPv4, router receives the packet with large MTU. If fragmentation is needed, the router itself fragments the packet. In IPv6, networks only and only sending host will perform fragmentation. Remember, that's the difference. If packet arrives at the router that is larger than supported MTU, router in IPv6 network will return ICMP version 6 packet too big message. So this ICMP version 6 specific message is called packet too big. So unlike IPv4 and IPv6 only sending host will do the fragmentation, and if packet arrives at router and it has larger MTU than the one supported, then router will return ICMP version 6 packet too big message. Next up, what we know as convergence in networks. Convergence is in fact when a network has complete and accurate information about the entire network path. So according to this, convergence time is how fast network devices can react to a change and reach the state of convergence after a topology change. So fast convergence time is what we're looking for, we are aiming at. Which two factors can influence convergence time for a routing protocol? Two important factors to remember. One, fine-tuning routing protocol timers. As we will see, with different routing protocols, we're going to have different timers. And fine-tuning those timers helps with convergence time. Next, and the second factor is route summarization. Enabling route summarization helps with convergence time. Why? Because route summarization results in less frequent and smaller updates. Lower convergence time comes as the result, and it has reduced routing overhead, which improves stability and scalability of the network. Because with reduced overhead, what we mean is reducing the routing information exchange between routers and maintained on routers. And if we can reduce them, then we increase the stability and also scalability, and we bring down the convergence time. Next up, more details about route summarization. Where do we get IP addresses from? Well, Internet Corporation for Sign Names and Numbers, ICANN, with Internet Sign Numbers Authority, IANA. These two are responsible for allocating address ranges to regional Internet registries known as RARs, and then also these two organizations, these two standards organizations, also allocate autonomous system numbers, ASNs, and they do protocol assignments and domain name service, DNS root zone. All these naming and numbering and assignments are done by these two organizations. Then when we got the IP addresses and when we define our subnets, route summarization helps us in order to group contiguous networks together. So that's the job of route summarization. It advertises all these contiguous networks using a single summarized route, and that's why we call it summarization. It decreases the number of entries in routing updates, firstly, and therefore, secondly, reduces bandwidth utilization for routing updates. If you have less number for the entries in updates, then you consume less bandwidth, so reduces bandwidth utilization for routing updates. And thirdly, it results in faster routing table lookups. If you have less entries, you consume less bandwidth, and your lookups are faster. So thirdly, it results in faster routing table lookups. We should know how to determine summary static routes out of a set of contiguous networks. So we use the same method here for summarization, for route summarization. It's as if we want to determine summary static routes for a couple of networks. We write out these networks that we want to summarize in binary. Then we find the subnet mask for summarization, start from the far left bit, and working from left to right, we try to find all the bits that match consecutively. That is gonna form our new subnet mask. 2 points here to conclude. Remember, we don't have automatic summarization OSPF, and with EIGRP, we are having manual summarization on a specific EIGRP interface. That's important. Just to recap, route summarization, as expected, less frequent and smaller updates. So remember, summarization reduces the number of updates and also their size, as we have less entries in the updates. This has a benefit. It brings down the convergence time, it lowers the convergence time, and then we can say that this reduced time for convergence is because of the reduced routing overhead, because we have reduced routing information to maintain and to exchange between routers and unrouters. And in this way, we improve the stability and also the scalability of our network infrastructure. What you see in this slide on the top right hand side, the figure, the contiguous subnets you can see, they're all summarized with one summary address 10.12.0.0/21. The point is, if one of these subnets on the left hand side, let's say 10.12.6.0, if it goes flapping, if it becomes unavailable, what would happen? Well, the summary won't get affected. So in the event of one given subnet, let's say this one becomes unreachable, router A does not need to inform the neighbor about the unreachable prefix. Why is that? Because the summary route is not affected by the network change, and that's an advantage that we have with summarization. So recall and remember. Summarization reduces number of updates exchanged. Next topic, we want to talk about different network types. We have three of them here, and there are more like loopback networks. We don't have them here. So point-to-point, the first category, the first type of network. Remember, these are important later when we go to OSPF. Network types are very important. So point-to-point here, then we have broadcast networks, and then we have non-broadcast, multi-access, NBMA, third type. Point-to-point network, P2P, a network that connects a single pair of routers. And a very famous example of that is a serial link, an example of a point-to-point connection. Second network type, here we have broadcast networks. And the reason that we call them broadcast because of the capability that they have, the capability to address a single message to all of the attached routers. This capability is called broadcast. And a router that can connect many routers with this capability is inside broadcast network. A very famous example of broadcast network is Ethernet, and the third type of network types that we see is non-broadcast multi-access NBMA network. NBMA network are the focus of discussion now. NBMA networks, they can support many routers, but they don't have broadcast capability. So they support many, but not broadcast capability, remember. And if NBMA networks, they don't have broadcast capability, that means that the sender, in order to support many, needs to create a copy for each recipient. So sender creates a copy for each recipient. And two very famous examples of NBMA networks are frame relay networks and ATM networks. So in these two, ATM and frame relay, the sender needs to create an individual copy of the same packet for each recipient if it wishes to inform all the connected routers in these networks of that packet. We see different network types here, and the reason for this is that routing, it does not have any problem when it comes to point-to-point or broadcast networks. So no difficulties for routing at all in point-to-point or in broadcast network types. But for non-broadcast multi-access NBMA networks, routing has problem and needs additional configuration. And that's why I explain different types of networks first. So routing protocols with NBMA networks, they need to be adapted because of two important issues. First one is neighbor discovery in NBMA networks, and secondly, the broadcast replication, the need to broadcast replication because of the lack of broadcast in NBMA networks. So while point-to-point and broadcast networks, they do not present any difficulties for routing protocols, NBMA networks, they introduce several challenges. One challenge that we want to see with the distance vector routing protocols is the split horizon behavior. We see shortly why we need to disable split horizon with distance vector routing protocols. Let's first see what split horizon is at all. It is, in fact, a loop prevention mechanism. Split horizon is a loop prevention mechanism used in distance vector routing protocols. So that simply means with split horizon, what we mean is we want to prevent the transmitting of information that is received on a specific interface from being forwarded or from going out of the same interface towards other neighbors. A good example of that is seen in the figure towards the bottom of this slide. From right hand side, the routing update is coming from first router on top right hand side 10.1.1.2/24 interface. That routing updates. It's a frame relay NBMA network. It comes over one single physical interface on a different sub interface. But when it gets to the route on the left hand side, then left hand side router is going to block forwarding the same routing update because of the enabled split horizon. And because of this, other neighbors there or other routers in this frame relay NBMA network like 10.1.1.6/24 or 10.1.1.10/24, they're not going to hear about that routing update. That's why enabled split horizon on a frame relay NVMe network is problematic, and that's why we said there are issues with routing on NVMe network, and you see one issue here with neighbor discovery. So that means, for instance, the stance vector routing protocols, they need additional configuration. In this case, we need to disable split horizon, though it's a loop prevention mechanism used by DV protocols, but we need to disable it now. Also, with link state routing protocols, we also have a neighbor discovery problem on NBMA. With link state protocols, LS, we also need additional configuration because routing protocols like OSPF, they want to be able to be discovering the neighbors automatically, but OSPF over NBMA neighbors, they're not automatically discovered, and therefore it's your job to statically configure neighbors for OSPF over NBMA, for which you need additional configuration. So additional configuration is required for you to statically define OSPF neighbors in NVMe networks, and that's why we have neighbor discovery issue. So you have seen neighbor discovery issue with stance vector routing protocol as a result of enabled split horizon, and also you have seen neighbor discovery issue with link state routing protocols because you need to statically define and configure neighbors, and they are not automatically discoverable anymore. NBMA and routing also have a second category of problems to do with broadcast replication, and for this, as we will see shortly, we need to configure the designated router for OSPF DR router sometimes manually, because OSPF treats NVMe like Ethernet by default, like a broadcast network by default. And since this is the default behavior of OSPF towards NVMe, sometimes you need manual and statical intervention with the routing to make it work properly. We have a very important example or instance of this discussion, what you see in this figure as well, hub and spoke frame relay scenario. So we have hub in the center, and hub is connected to different spokes. and they're all the underlying network of all these nodes are frame relay. Hub and spoke frame relay topology can have two different architecture. We can have point-to-point hub and spoke, point-to-point sub-interfaces hub and spoke frame relay topology, and we can have point-to-multi-point sub-interfaces frame relay topology. If we have point-to-point sub-interface for hub and spoke frame relay topology, then we're going to have single PVC and single physical interface. We call that PVC stands for permanent virtual circuits. With permanent virtual circuits, if we have single of them over a single physical interface, then a split horizon is not a problem, because at the end of the day it is a point-to-point network. So point-to-point sub-interface hub and spoke topology at the end of the day acts as point-to-point physical network, and that means that split horizon is not a problem if there is a single PVC and a physical interface, because as I said, this network would be point-to-point. The second architecture, or the second type of architecture that we have with point-to-multi-point sub-interfaces for hub and spoke frame relay topology, then we're going to have multiple PVCs over a single physical interface. In this case, when a spoke router sends an update to the hub router is connecting multiple PVCs or multiple permanent virtual circuits over a single physical interface. And the hub router that receives the update on this physical interface cannot forward it through the same interface to other spoke routers because of the split horizon, or because of the enabled split horizon. That simply means broadcast replication is required. So what you see in the figure here is an instance of point to multi-point sub-interfaces for hub and spoke frame relay, with hub residing on the left hand side and spokes on the right hand side of the figure. What we see here is that when a spoke on the right sends an update to the hub on the left, that is connecting multiple permanent virtual circuits, multiple PVCs over a single physical interface, as exactly can be seen in this figure. The hub cannot forward the update towards other spokes because it's blocked forwarding because of the split horizon out of the same interface on which we have received the update. And that means the hub on the left hand side needs to support additional configuration for broadcast replication. So broadcast replication is required with point to multi-point sub-interfaces. One clear observation here is that with point to multi-point sub-interfaces, one subnet is always shared between all virtual circuits. So 10.1.1.0/24. This is the single subnet to be shared between all virtual circuits or VCs. So the takeaway point for you is that for NBMA, routing over MBMA networks. Both EIGRP and OSPF, they need additional configuration to support this underlying technology. Also remember where we had the point-to-point subinterface for hub and spoke frame relay topology. We don't have routing issue with that when we have single PVC per single physical interface, because split horizon can work fine, no problem there. But when we have point to multi-point sub-interfaces for hub and spoke frame relay topology, we need additional configuration, and we also need broadcast replication. To wrap up, non-broadcast multi-access networks issues. Two category mainly if we want to categorize them: neighbor discovery and broadcast replication. Neighbor discovery is problem with distance vector routing protocols like EIGRP, whereby we have split horizon enabled. We need to disable them manually if we are on NBMA network. Link state routing protocols, they have problem with NBMA. OSPF treats NBMA as Ethernet, so treats a non-broadcast network as a broadcast network. Therefore, you need to intervene and statically define neighbors for OSPF. Then we have broadcast replication, and we have seen in the previous example, we need to set manually the designated router DR for point to multi-point frame relay scenario. In the previous slide, bottom of the page, the figure that we had, because that topology, all the routers, they support multi-point connections or a single physical interface that is terminated at multiple PVCs, permanent virtual circuits. Router must therefore replicate broadcast packets as there is no broadcast capability here. Of course, this broadcast replication here comes as a direct issue of NBMA network, but it also results in another issue indirectly, that is latency. Two scenarios, we already saw that point-to-point sub-interfaces with frame relay NBMA topology, and also point-to-multi-point sub-interfaces with frame relay topology. With point-to-point, each subnet between two routers uses its own subnet mask or network address. What you can see in this figure, unlike the previous figure, is a point-to-point subinterface configured between each of these two routers. So again, we have a hub and spoke frame relay NBMA network, but as you can see, we have different subnets. Each subnet between two routers, let's say the one on the left and each one on the right, they have their own subnet with their own network address, with their own subnet mask. So 10.1.1.0/30, 10.1.1.4/30, and 10.1.1.8/30. These three subnets are used between one hub on the left and three spokes. But more importantly, remember with point-to-point sub-interfaces, we don't have a routing issue. Single PVC and single physical interface, split horizon is not a problem because the connection is point-to-point. But point-to-multi-point sub-interface is the one that we had in the previous slide. As you see, only one subnet is defined between all nodes, between all hub and spokes, and that's why we have problem with we need to disable split horizon, and also EIGRP OSPF need additional configuration in order to discover neighbor and also to replicate broadcasts. We have routing across MPLS VPNs, two famous scenarios, whereby the ISP cloud in the middle, it provides only layer 2 service across backbone, and secondly, whereby we have the ISP cloud providing layer 3 service across backbone. When we deploy routing over layer 2 MPLS VPNs, the one that you see on the left hand side at the bottom of this slide, neighbor adjacency with the routing is established directly between router 1 and router 2, as if there is no cloud or there is no ISP cloud in the middle, because the whole thing in the middle is a layer 2 backbone. So R1 and R2 can directly get connected with the same subnet. So that's why the connectivity of the ISP cloud or the backbone of the network here is shown or illustrated as one big switch. So what R1 and R2 they see in the middle is in fact one big switch. That's why they are both on the same subnet, and they can get directly connected and routing neighbors. This is not the case with layer 3 MPLS VPNs, where we provide layer 3 service across backbone. If we have layer 3 MPLS VPN, then ISPs are expected to participate in routing as well. So ISP edge routers, not shown here, they need also to establish neighbor adjacency at each side with R1 and with R2. So if we consider the ISP cloud in the middle, and if we consider inside this box we have two ISP edge routers, let's say provider edge 1 and provider edge 2, then R1 P1 and R2 P2, they need to form adjacency, neighbor adjacency as well, and ISP needs to participate in routing, and R1 P1 is on a different subnet than R2 P2, so separate subnets between R1 P1 and R2 P2. This is again unlike what we had with layer 2 MPLS VPNs. So with layer 3 MPLS VPNs, neighbor adjacency is established between R1 and the closest provider edge P router, and also between router 2 R2 and its closest provider edge router. Next up, choosing a path. The very important question to ask here is that how do we select which path to take? So what are the choice criteria by which we can say that specific path is taken in order to get to a specific destination. For a path to be valid, there are three conditions or three criteria to check. And they are in the order of preference. The first and the most important one is that the path must be accessible. So a router cannot choose a path which is shut down administratively. So the first and the most important one, the path must be accessible. So no shutdown command should be issued under the interface. And this is the first priority, and this is the first criterion that the router must check before forwarding out a packet. The second criterion, then the router will select best route based on the lowest administrative distance, AD. We go into more details for AD shortly. And the third criterion to check if administrative distance, AD or ADs for more than one route, let's say for two routes, are the same, then we look at the metric. So the third criterion to check is the metric. Let's see what AD is. AD is used in order to rank the believability or trustworthiness of static and dynamic routing protocols. Once again, we rank believability and trustworthiness of static and dynamic routing protocols. In other words, static and dynamic routing protocols, they are assigned a value called AD in order to rank trustworthiness. The lower the AD, the number, the more believable the route or the path is. So remember, AD is the trustworthiness of a learned route. The lower the better, and the more trustworthy the source of a learned route is. We need to remember AD is associated with directly connected interface, that is 0, AD of static route, that is 1. Doesn't matter if static route is configured with an outgoing interface or with an XHop address command. Whichever you go with, the AD is 1. Static route is always 1. AD for EIGRP summary route is 5. External BGP routes, they have AD of 20. Internal EIGRP 90. OSPF AD is always 110. ISIS 115. RIP routing information protocol has the AD of 120. So you can easily say that internal EIGRP is preferred over OSPF and OSPF is preferred over RIP. So the lower AD, the better. External EIGRP, they have AD of 170. Internal BGP, IBGP with AD of 200. Default static route, provided that it is LAN through DHCP, has the AD of 254. In other words, DHCP is encouraging you not to use the default static route advertised by him in case that you have any other way out of your network. So to make it less attractive, DHCP assigns a very high number to AD, 254. And if a source for a learned route is unknown and therefore unused, then the AD is 255. We are not interested at all. We don't trust the source at all. Next up, we want to see what floating static route is and what it means. If the default static route is issued from ISP, then it's called floating static route. It's floating static route, or it's floating because it has a high AD of 254, which simply means that ISP is telling you that use this floating static route, or let this floating static route become default route only if you don't have any default route being learned from any other routing process with lower AD. In other words, the ISP is telling you that use this default route as a backup solution. If you can get any default route from any other routing process or any other routing source with lower AD than 254, then please go with that. If you don't have any other default route being learned from any other routing process with lower AD, then okay, you can use it, but not as the plan A, but as plan B. So floating static route, that word floating means that the AD is 254. And this is unlike the static route. When you define a static route, the AD is 1. So it's highly preferred. But if the default route is being advertised by ISP, then it's gonna have the AD of 254. But used only if default route is not learned from any other routing process. Next up, we're going to talk about generic routing encapsulation, MGRE, or multi-point GRE. We want to talk about a technology called DMVPN and its components. DMVPN, or Dynamic Multi-Point Virtual Private Networks, has three components to discuss here. MGRE, the one that is the topic of discussion here, is one of them. IPsec is the second one, and also a protocol called NHRP, Next Hop Resolution Protocol, is another component for DMVPN. What is DMVPN? DMVPN is in fact a solution that offers the capability to dynamically establish hub-to-spoke and spoke-to-spoke IPsec tunnels, and as a result to reduce latency and optimizing network performance. Traditionally, we only had hub-spoke communication. Now, thanks to DMVPN, we can have hub-to-spoke as well as spoke-to-spoke secure communication thanks to IPsec tunnels, and we can have that quite quick without latency and with optimized performance. Three benefits of DMVPN needs to be discussed, but before that, let's just review what traditional or normal GRE is. Generic routing encapsulation GRE is considered by itself a non-secure VPN tunnel solution, whereas our DMVPN is a secure tunneling solution. GRE is a non-secure VPN tunnel solution. It's originally been developed by Cisco. GRE can encapsulate a wide variety of routing protocols inside IP tunnels. That's important to remember. Additionally, GRE can be also used in order to smooth transition from IPv4 to IPv6. For for GRE tunnel to work, the source needs to be able to route to destination. So that's a very important criterion to meet for a GRE tunnel. Source should be able to ping the destination. So source has to be able to route to destination. After that condition is met, then we can establish GRE. Dynamic multipoint VPN, however, uses multipoint GRE. And thanks to multipoint GRE, we can ensure the scalability of the DMVPN solution, because now we can dynamically establish not only hub to spoke but also spoke to spoke IPsec secure tunnels. The first obvious benefit of DMVPNs is the reduction of configuration on hub router, unlike the traditional VPNs. So hub router configuration is reduced because traditionally the individual configuration of a GRE tunnel and IPsec configuration also, they would need to be defined for each individual spoke router. In other words, we need to do some changes on the hub and also some changes on the current spokes if we add a new spoke, for instance. With DMVPN, there is no need to change anything on the current spokes or on the hub side when a new spoke is added to the scenario. This is because DMVPN feature enables the configuration of a single MGRE tunnel interface, so a single multipoint GRE tunnel interface, and a single IPsec profile, so single tunnel interface from that supports MGRE and also single IPsec profile on the hub router is enough to manage all spoke routers. So unlike the traditional one, we don't need to have separate configuration for each individual spoke. A single tunnel interface and a single IPsec profile on the hub would suffice in order to manage all spoke routers. So as you can see in the slide, MGRE ensures scalability of a DMVPN solution, and also you can see that MGRE does this thanks to having a single GRE interface, or better to say a single MGRE tunnel interface to be configured on a hub router to support multiple remote peers. But when we say DMVPN offers the capability for dynamically establishing hub to spoke and spoke to spoke IPsec tunnels, how can the MVP do that in a dynamic manner? In order for spokes to dynamically establish peering relationships, either with hub or with other spokes, they need, or let's say the system needs to learn the IP addresses of the peers. So how to learn the IPs of peers, other peers. In order to do that, devices that are using multi-point GRE, MGRE, they are relying on NHRP or Next Hop Resolution Protocol, as I said, to build dynamic GRE tunnels. So this dynamic GRE tunnel is facilitated by NHRP protocol. The job of NHRP is in fact to discover IP address of the device residing at the end of the tunnel. Lastly, remember MGR interfaces, they not only support unicast but also support multicast and broadcast traffic. So out of three benefits of DMVPNs, we have seen the first one, hop router configuration reduction, and the second one is the support for dynamically addressed spoke routers. In other words, with DMVPN, as I said, using NHRP, Next Hop Resolution Protocol, spokes automatically and dynamically they register themselves with the hop, or better to say, they register their IPs with the hop. So hop does not need to know advanced knowledge of the IP addresses of the spokes, because hop knows that as soon as spokes come up, they come to us and they register to us themselves. So that means support for dynamically addressed spoke routers when using point-to-point GRE and IPsec hub and spoke VPN networks. As we had in legacy scenarios, it is important to know the physical interface IP address of the spoke router when configuring the hub router. With DMVPN, however, it enables spoke routers to have dynamic physical IP address for interface, and they use NHRP, Next Hop Resolution Protocol, in order to register the dynamic physical interface IP of the spoke router with the hop router. And that brings us the second obvious benefit of DMVPN, which is the support for dynamically addressed spoke routers. Because whatever the address for spoke routers are, we know that they're going to come and tell us themselves thanks to NHRP. And this leads to the third obvious benefit of DMVPN, because we know that GRE uses NHRP in order to configure and resolve the peer destination address. After this resolution happened, that means that IPsec can get initiated automatically without any peering configuration or IPsec peering configuration needed to be done on the hop router thanks to NHRP. That means the third obvious benefit of DMVPN is automatic IPsec initiation, because when GRE uses NHRP, this feature allows IPsec to be immediately triggered to create point-to-point GRE tunnels without any IPsec peering configuration needed. So you see that this NHRP, in fact, it brings two different sets of advantages for us. It's the support for dynamically addressed spoke routers, as well as the automatic IPsec initiation without peering IPsec configuration needed. These two are the benefits of NHRP. It is important to remember that NHRP, in fact, is a client-server protocol. The hop acts as the server, and spokes are the clients. NHRP is used by routers in order to determine the IP address of the next hop in IP tunneling networks. and that's why it's called Next Hop Resolution Protocol. When a spoke router initially connects to the DMVPN network, as we said, it registers its inner tunnel or inner address, which is the tunnel address, and outer address or physical interface address with the hub. So two different things: inner or tunnel address, outer or physical interface address. And spoke initially registers both inner tunnel or tunnel address and outer or physical interface address with the hub router. And the hub router is NHRP 7, remember. This registration then enables MGRE or multi-point GRE interface on the hub router to build a dynamic GRE tunnel back to the registering spoke router without having to know the branch tunnel destination in advance. And that's why it's called dynamic GRE tunnel. That means that NHRP creates a mapping for a tunnel IP to physical IP. So this mapping, tunnel IP to physical IP mappings, are created by NHRP for each spoke at the hub router. Here, I would like to summarize discussions we have had. We've talked about the benefits of the MVPNs, how it reduces the configuration required on the hub router, how it provides the support for dynamically address spoke routers, and the way that it helps with automatically initiating IPsec with peers without needing them to have a certain configuration, unlike the traditional IPsec tunnels. So, in summary, configuration of the hub router is shortened and simplified due to the fact that it does not need to have GRE information or IPsec information about the peer router or routers in advance, and all the information required is already learned dynamically through a protocol called NHRP, Next Hop Resolution Protocol. Three components for DMVPNs: MGRE or multi-point GRE, we have NHRP and IPsec. Three characteristics of MGRE: only one tunnel interface is enough to support multiple GRE tunnels. So one tunnel interface with multi-point GRE is enough. Second characteristic of MGRE is its ability to dynamically build GRE tunnels, thanks to NHRP, of course. And then the third characteristic of MGRE is its support, or the support that it provides for multicast and broadcast as well as unicast. When we use NHRP inside MGRE, so NHRP in collaboration with MGRE results in mapping inner tunnel IP address to the outer transport IP address. And when we use this in a hub and spoke DMVPN deployment, that means that no GRE or IPsec information about a spoke is configured on the hub router. All we need to do is that we need to configure spoke router for the GRE tunnel with information about the hub, and that means through NHRP We define hop as the next hop server, for the spoke. Later, when the spoke router starts up, it automatically initiates the IPsec tunnel with the hop router, thanks to NHRP, because spoke uses NHRP to notify the hop of its current physical interface IP address. That's why it's dynamic. It can change because no matter which physical interface IP address spoke is using, he is going to uh, inform the hop or the server of that address anyway. When you add a new spoke router to a DMVPN deployment, you do not change, as I said, the configuration on the hub or any other current spoke router. The new spoke router is configured with hub information, and that's it. When it starts up, the spoke dynamically registers with the hub. The dynamic routing protocol propagates the routing information for the spoke to hub, and also hub propagates new routing information to other spokes about this new spoke, and it also propagates the routing information from other spokes to the new spoke. So who is in charge of updating the new spoke of other spokes? Hub. That's it. So, in short, two obvious advantages of Next Hub Resolution Protocol. First, it enables spoke to have dynamic physical IP or inner tunnel IP to outer transport IP, this mapping. So, inner to outer or tunnel to transport IP mappings. This can be done dynamically because spokes registers the IP with hub through Next Hop Resolution Protocol NHRP. Secondly, we can use NHRP to resolve peer destination address, and as a result of that, we can allow IPsec to be immediately triggered in order to create point-to-point GRE tunnels without any IPsec peering configuration needed on the peer. We don't need to wait anymore. We can start right away as soon as a node comes up to form IPsec with our peers. The third component for the MVPN is IPsec, and we all know about IPsec and the protection that it provides for network layer and above. So it protects IP layer and above IP layer. There is no protection with IPsec for layer 2. It can only protect IP layer and up, transport and user data, and it cannot extend its protection service to data link layer. When we have IPsec in tunnel mode, recall that it creates a new external IP header that contains the IP address of the tunnel endpoints. And when we say tunnel endpoints, that can be routers, that can be VPN concentrators. But anyway, it contains the IP addresses of the tunnel endpoints inside the new external IP header. The exposed IP address in tunnel mode, in fact, is the tunnel endpoints, not the device IP addresses that sits behind the tunnel endpoints. Next up, we want to talk about point-to-point protocol, and in particular point-to-point protocol authentication. Point-to-point protocol, PPP, how it does and performs authentication. It defines what we know as LCP, link control protocol LCP in order to negotiate authentication between two peers before allowing network layer or layer 3 protocol to operate. This is important. PPP defines LCP before allowing layer 3 protocol to operate in order to negotiate authentication before layer 3 operate, and bear in mind that it's in fact PPP that defines LCP, and the purpose is to negotiate authentication before allowing layer 3 protocol to operate. There are two point-to-point protocol authentication protocols. We've got POP and we've got CHOP. With POP, password authentication protocol, and with CHOP, challenge handshake authentication protocol. We need to know which one is more secure and how they work. POP is basic two-way authentication process, whereas CHOP is more secure and it's three-way. It involves three-way handshake. So CHOP is more secure than POP. POP is basic two-way authentication with plain text username and password being sent, whereas CHOP uses periodic challenges in order to make sure that the source is still valid and is considered a secure PPP authentication protocol because it has encryption, so three-way encrypted, and also periodic challenge to make sure that the source is still valid. These three are the characteristics of CHOP. Next up, we want to talk about routing information protocol, RIP and RIP-NG. RIP uses hop count, as you know, the number of routers, as the metric. That means if a device has two paths to destination, the path with fewer hops is going to be chosen as the preferred path to forward traffic. In RIP, the maximum number of hops allowed is 15, and that makes 16 or more as unreachable. So if a network is 16 or more hops away, that means the router considers that network to be unreachable. Very important to remember the point that in RIP-NG, RIP next generation for IPv6, unlike RIP version 1 and unlike RIP version 2, the sending router already considers itself to be one hop away, and that means RIP-NG routers, they're going to add one hop to the metric when they receive the RIP-NG update. This is the behavior of RIP-NG and not a RIP version 1 or RIP version 2. Here I'm going to talk about EIGRP, Enhanced Interior Gateway Routing Protocol. EIGRP relies on an algorithm called diffusing update algorithm, dual, and the reason that we using dual for EIGRP is not only to find out the best loop-free path to a subnet, but also to find the best loop-free backup path to the same subnet. And that backup path should be able to be used as soon as the main primary route goes down, so to be used immediately as soon as a link or route failure happens. And all these is feasible and possible thanks to dual to achieve rapid convergence as soon as a network change happens. We're using dual. The first lesson to know about EIGRP is fast convergence that EIGRP has. Even if no appropriate route exists in the local routing table and no appropriate backup route exists, EIGRP can query its neighbors to discover an alternative route. So it's a very active routing protocol. These queries that EIGRP makes are propagated until an alternative route is found or until it is determined that there is no alternative existing there. And all these bring fast convergence for EIGRP. For EIGRP to perform neighbor adjacency establishment, there is no such a need that both routers they need to have the same timer, so they can have differing timers, even though we don't have such a situation with OSPF and timers must match. With EIGRP, even with different timers, two routers can establish neighbor adjacency. EIGRP relies on 5 types of packets in order to form its different tables, like topology table, like routing table, and establish complex relationships with different EIGRP neighbors. These 5 types of packets are hello packets, acknowledgement, update, query, as I just spoke of, and reply. At the very beginning of the scenario, we use hello packets in EIGRP in order to discover neighbors, and that happens before establishing any adjacency with EIGRP neighbors. Remember, EIGRP hellos are sent as multicast, and EIGRP routers must first form neighbor relationships before exchanging the second type of EIGRP messages, EIGRP updates. EIGRP updates, they convey routing information to known destinations. In fact, we communicate the routes that we have used to converge ourselves to our neighbor. EIGRP updates, they use both multicast and unicast. EIGRP updates are sent as multicast when a new route is discovered or when the convergence is completed, meaning that the route becomes passive. But upon EIGRP startup, as soon as EIGRP goes up, we use unicast EIGRP updates in order to synchronize our topology tables with neighbors. So at the very beginning of the scenario, we use unicast for synchronizing EIGRP topology tables with neighbors, but later, when a change occurs, let's say a new route is discovered, EIGRP updates are sent as multicast. No matter which EIGRP update messages, they are sent reliably thanks to RTP protocol between EIGRP routers. In fact, the delivery of important routing information with EIGRP is always through RTP or over RTP, let's say. And this is very important to remember when we say important routing information. Well, we don't consider hello or acknowledgement itself, these two, as important, but update, query, and reply packets to neighboring routers are considered important routing information contained messages. So EIGRP reliability mechanism ensures the delivery of important routing information such as update, query, and reply packets. Reliable Transport Protocol RTP is responsible for guaranteed and ordered delivery of EIGRP packets with the use of sequence and acknowledged numbers. But here with RTP, we do not have any fancy windowing or congestion control mechanism, the ones that we have with TCP, because only one packet will be sent at a time. And also remember, RTP transmission supports not only unicast but also multicast. So transmission of both multicast and unicast packets are supported with RTP in EIGRP. Next, how do EIGRP routers get a specific information from a neighbor? They use query message type. So query is used to query other EIGRP neighbors for what we know as feasible successor, and we will see the definition for it shortly. For now, just bear in mind that the best route with the lowest metric in EIGRP is called successor, and successor is the next hop to get to that specific subnet, and the whole thing is forming the best route. And if the best route goes down, meaning that successor is not valid anymore, then we have feasible successor as the backup. So if dual, which is the EIGRP algorithm, is to recompute a route in which the router does not have a feasible successor or a backup path, then EIGRP uses query message type. EIGRP queries are sent reliably again, and they're using multicast transmission. So far we have seen update messages. They're transmitted as both unicast and multicast. And now we have seen EIGRP queries. EIGRP queries are sent reliably using multicast. Next type of EIGRP message is EIGRP reply message type. And as you would expect, it is sent as the response to an EIGRP query packet we have just talked about. EIGRP replies are sent reliably again using unicast. So far we have seen unicast updates, multicast queries, and remember now EIGRP replies are using unicast only in response to EIGRP query packets. Then we have the fifth EIGRP message type, that is acknowledgement, and is used in order to acknowledge EIGRP updates, to acknowledge EIGRP queries, and to acknowledge EIGRP replies, because EIGRP believes that update, queries, and replies, they contain important routing information. So these three message types are acknowledged, and acknowledgement in fact is a hello packet of EIGRP that contains no data and a non-zero acknowledgement number. So inside hello packet we have acknowledgement number. If it is 0, the packet is hello packet, and if it's non-zero acknowledgement number with no data inside the packet, then that packet is acknowledgement packet. And remember, acknowledgement for EIGRP is sent as unicast. So to wrap up, we have seen multicast hello, we have seen unicast or multicast update, we have seen multicast query, we have seen unicast reply to in response to queries, and then now we have seen the fifth type, that is unicast acknowledgement. Talking of reliability, we only consider reliable transmission for 3 EIGRP message types, that is update, query, and reply. We have previously seen that EIGRP dual algorithm, it tracks all the routes that are advertised by neighbors and uses what we know as composite metric of each route in order to select the best loop-free path and also the best loop-free backup path. So the best loop-free path or the best route to be calculated by dual and delivered to routing table is the one that has the lowest metric, and metric in the context of EIGRP is known as feasible distance. So the lowest metric from the current local router to a destination, a subnet, is the feasible distance to that destination. We have different tables that EIGRP uses in order to calculate the best route and the best backup route. Topology and routing table. We start with knowing how EIGRP builds its topology table. The overall process for building EIGRP topology table is relatively straightforward. So EIGRP defines some basic topology information about each route for each subnet for unique prefix length, and this basic information includes the prefix length, and metric information, a few other details. This topology information is exchanged between EIGRP neighbors, with each router storing the learned topology information in its respective EIGRP topology table. Next step, EIGRP is now able to analyze the information stored in topology table or topology database, we call it as well, in order to choose the best route for each unique prefix and length. This is important to remember that unlike OSPF, EIGRP uses simple topology data. So EIGRP uses much simpler topology data than OSPF does. And this is because OSPF is a link state protocol that must describe the entire topology of a portion of a network with its topology database. Whereas EIGRP, essentially as an advanced distance vector routing protocol, does not need to define nearly as much topology data as OSPF does, nor do EIGRP routers need to run the complex SPF algorithm, shortest path first algorithm. That's why we say EIGRP uses much simpler topology data than does OSPF. So far, we have seen that before a router can send EIGRP topology information to a neighbor, it must first have its own topology table created in the first place. Routers can, of course, learn about subnets and associated topology data from neighboring routers later, However, to get this process started, each EIGRP router needs to add topology data for some prefixes that it is aware of, so that it can then advertise these routes to its EIGRP neighbors. A router's EIGRP process therefore adds subnets to its local topology table without learning the topology data from an EIGRP neighbor from different sources. Firstly, prefixes of connected subnets for interfaces on which EIGRP has been enabled on that router using the network command. This forms the first source for seeding the local EIGRP topology table. So as soon as you issue the network command on an interface, let's say, then the connected subnet for that interface is going to be added to the local topology table. This added topology table entry also describes the interface bandwidth of the associated interface. It lists also the delay of the associated interface. And if we are using default setting, then we're going to have a load that is equal to 1 and reliability that is equal to 255. Remember, that is the default values for metric calculation, and that can be later overridden. So the first source of information is prefixes of connected subnets for interfaces on which EIGRP has been enabled. If we have used neighbor command, then that is going to form the second source of information to seed topology table on the local router, prefixes of connected subnets for interfaces referenced in an EIGRP neighbor command. And thirdly, we may have redistribution in our scenario, prefixes learned by the redistribution of routes into EIGRP from other routing protocols or routing information sources. That is going to shape the third source for information to seed the EIGRP topology table on the local router. After a router adds such prefixes to its local EIGRP topology database, that router can then advertise the information about certain prefix along with other topology information associated with each prefix, such as metric, to each working EIGRP neighbor. So once more, the whole scenario starts from each router adding any learned prefix information to its topology table locally, and then that router is going to advertise the new information to other neighbors. If any new information comes up, any changes or any failure, let's say, then that router is going to advertise that very new information also to other neighbors. Eventually, we're going to have all routers in the EIGRP domain learn about all prefixes unless some other features such as route summarization or route filtering, for instance, alters the flow of topology information. If we don't have that, then all routers in EIGRP domain are going to learn about all prefixes. So, to recap, We have built our topology table first locally, and then we want to exchange it with an EIGRP neighbor. How this is done: exchanging topology information is done using update messages. So EIGRP update process is going to take place when EIGRP neighbors at very beginning become neighbors. They begin exchanging this information. As soon as a neighbor first comes up, the routers are going to exchange full updates, meaning that the router exchanges all topology information it has. But remember, that is going to only happen once. After all prefixes have been exchanged with a neighbor, the updates cease with the neighbor if no changes occur in the network. Meaning that we are not going to have any subsequent periodic reflooding of topology data in EIGRP, unlike OSPF. So the first rule is, as soon as a neighbor comes up, exchange of full updates is going to happen. The second rule for EIGRP update process is that if something changes later, for example, one of the metric components changes, or a link fails, or a link, an already failed link, let's say, is now recovered, or new neighbors advertise additional topology information, for instance, at that moment the routers send partial updates. So no more full updates, but partial updates about only the prefixes whose status or whose metric components have changed. Next rule is, if a neighbor, an EIGRP neighbor, completely fails and then recovers, what is going to happen is that a new neighbor adjacency is going to be formed. So that means, again, we're going to have exchange of full updates, and full updates exchange occurs over these adjacencies. Fourthly and finally, EIGRP uses a split horizon. A split horizon rule is applied by default on most interfaces in EIGRP, which impacts exactly which topology data EIGRP is sending during both full updates as well as partial updates. That means that if, let's say, the currently best route for a prefix lists a particular outgoing interface, a split horizon causes EIGRP to not include that prefix in the update sent out that same interface. So once more, if the currently best route for a prefix lists or includes a particular outgoing interface, a split horizon causes EIGRP to not include that prefix in the update sent out that same interface. Let's say router 1, it uses subinterface serial 000.1 as outgoing interface for subnet 10.11.0.0/24. This rule in place means that we are not going to advertise prefix 10.11.0.0/24 in the update sent out the same serial subinterface 000.1. We are not advertising this associated prefix in update sent out the same sub interface. So let's summarize. We have created our topology table using the network or neighbor or redistribute commands. After creating local topology table on our local EIGRP router, then we need to exchange topology table with update messages to our EIGRP neighbors. That's the second step. And the third step now is to build routing table. So routing table is derived from the gathered information as a result of topology table exchanges. An EIGRP router builds IP routing table entries by processing the data inside topology table. And unlike OSPF, which uses a computationally complex SPF algorithm, EIGRP here uses a computationally simple process in order to determine which, if any, routes to add to the IP routing table for each unique prefix and length. The EIGRP topology table entry for each prefix and length not only lists the best path, the best loop-free route, but may also contain more possible routes. And each possible route lists the various component metric values, such as bandwidth or delay, and so on and so forth. In other words, not only the successor, but also the feasible successor. So not only the next hop router, but also the backup router. Inside EIGRP topology table entry, if the prefix is a connected subnet, for connected subnets, the database entry lists an outgoing interface. For routes that are not connected to the local router, in addition to an outgoing interface, the database entry also contains IP address of the EIGRP neighbor that advertised that route previously. So EIGRP topology table entry lists possible routes, plus for connected subnets we're going to have only outgoing interfaces, plus for not connected subnets we're going to have IP address of EIGRP neighbors in addition to the outgoing interfaces. And of course, other information related to metric. Now, this metric information inside topology table entry is going to be exchanged, and EIGRP routers later calculate an integer metric based on the metric components exchanged. Interestingly, with EIGRP, the router does this calculation, metric calculation, both from its own perspective and also from the perspective of the next hop router for that specific route. And that's why we're going to have feasible distance FD defined as an integer metric for the route from the local router's perspective, used by the local router in order to choose best route for that prefix. And secondly, we're going to have advertised distance AD or reported distance RD as an integer metric for the route from the neighboring router's perspective. So not from local router's perspective. This time with AD or RD, we are talking about what neighbor sees. The neighbor that told the local router about the route is intended with AD or RD. And as we will see shortly, this AD or RD are used, they are in fact the same thing, they are just different terms for the same concept. AD equals to RD. It is used by the local router when converging to a new route. How? Let's start with FD, feasible distance, or metric. Routers, they use FD in order to determine the best route based on the lowest metric, and use RD when falling back to an alternative route if the best route fails. And now we want to see how routing table information is derived from topology table information. When a router has calculated the integer FD or metric for each possible route to reach a single prefix and length, i.e. to reach a subnet, that specific router can then consider adding the lowest one, the lowest metric, or the lowest FD, let's say, to the IP routing table. So adding the lowest metric route to the IP routing table is the way that we form routing table out of topology table. Speaking of metric in EIGRP, remember that EIGRP only uses a composite metric. The way that EIGRP calculates the metric, assuming that we have default settings for metric weights for K values, is in a way that the metric calculation grows, meaning that it gets worse when the slowest bandwidth in the end-to-end route decreases. In other words, the slower the bandwidth, the worse the metric. And the metric calculation also grows or gets worse when the cumulative delay grows. Finally, bear in mind that the unit of measurement for bandwidth, for slowest bandwidth, is kilobit per second, and unit of measurement for cumulative delay is tens of microseconds, not microseconds, tens of microseconds. And with the default metric weights, we're going to have the formula 256 times 10 to the power of 7 divided by the slowest bandwidth plus cumulative delay for metric calculation. As I said, that's the default weights for K values. We may manipulate that, and if we manipulate the EIGRP metric calculation, that means that we are able to pick one route, let's say, instead of another. One specific route can be picked up, or secondly, we can tune these weights in order to have faster convergence. Next, we want to talk about optimizing the EIGRP convergence process. The design goal is that EIGRP is going to converge as quickly as it can without introducing routing loops. That's why we always prefer EIGRP thanks to its fast convergence. Many routing protocols, they support equal load balancing. EIGRP not only supports equal load balancing but also supports unequal load balancing, and that's important about EIGRP. It allows both spreading the load across multiple routes, and also it allows us to manipulate some features in order to improve EIGRP convergence. So in addition to spreading load across multiple routes, it supports improving EIGRP convergence. One reason for fast convergence of EIGRP, it is due to the use of feasible successors, as you have seen previously. If the main successor goes down, EIGRP quickly switches to feasible successor route, if there is any. And therefore, EIGRP advantages from fast convergence in case of any changes. We have seen feasible distance FD as the metric from that router's local router's, let's say, perspective. In addition to that, the other metric that we have discussed is RD reported distance, which is the integer metric from the perspective of the next hop router. That's why FD is known as the metric value for the lowest metric route to a particular subnet. Just to recap, for each prefix and prefix length, i.e. for each subnet, when multiple possible routes exist, the router chooses the route with the lowest metric or the smallest integer value for the metric as the best route. So smallest FD is chosen as the best route and is installed in routing table as well. Once again, EIGRP defines each such a route as the successor route for that prefix, and therefore defines the next hop router in such a route as the successor. So successor and next hop router, they are the same thing. EIGRP then creates an IP route for this prefix with the successor as the next hop router and places this route into the routing table. Successor and next hop router, they are the same concept. EIGRP routers use the reported distance RD value when determining whether a possible route can be considered to be a loop-free backup route, and this loop-free backup route is then considered as feasible successor, meaning that if successor or next hop router goes down, feasible successor takes over. Feasible successor therefore is called loop-free backup router. So successor, next hop router, feasible successor, backup router. For this to happen, this backup route must meet the feasibility condition. With EIGRP, a route that is not a successor route but meets the feasibility condition can be used when the successor route fails without causing loops, and that improves the convergence time, and that's why we call EIGRP to advantage from fast convergence. What is feasibility condition, FC? With EIGRP for a particular route, the case in which the reported distance is lower than the feasible distance, so RD smaller than FD, in this situation we say that FC is met, feasibility condition is met. In other words, our neighbor's metric to a specific subnet is smaller than our own local router's metric to that subnet, then feasibility condition FC is met. So a feasible successor, FS, is a neighbor who has a loop-free backup path to the same subnet as the successor if it satisfies the feasibility condition, and FC is met when that neighbor's reported distance to a network is less than the local router's feasible distance or metric to the same destination network to the same subnet. Just to recap, successors, feasible distance or metric should be higher than feasible successors, advertised distance or reported distance, and if that is met, then FC feasibility condition is met, and therefore we can choose that route as backup path. The very last bullet point here is when we don't have feasible successor and if FC is not met, That means that if current path is lost, router flags the route as active. And active in this context means that the EIGRP router does not have the current view towards that specific subnet because it just went down, the route went down, and that EIGRP router needs to start searching for new successor to get to the specific subnet. So remember, active means that there is a failure, and that failure is when we don't have feasible successor and the successor has gone down, and that means we need to start searching for new successor.